Hello students, it's a pleasure having you back in class. Today we are going to discuss on the study session 5. I hope and I want to believe that you enjoyed the last study session, which is on dynamics. We are going to be talking on elastic properties of materials. When you have studied this session, you should be able to define some terms. You should be able to explain elasticity, define Hooke's law, Young's, bulk, and shear modulus. Then you should be able to discuss molecular properties of fluids. First of all, we are going to start with definition of elasticity. Elasticity is an essential properties of material. It's simply the characteristics of a material that determines its response to an applied force or load. Typical example is a spring. Springs of all types are a sample of elastic bodies. When considering the fusion of a spring, you observe that a spring will respond to distortion force and then yield to its original shape after the distortion force has been removed. Take for instance, supposing this is a spring. By the time I applied force across its end, it will be elongated. And by the time I release it, it returns back to its original shape. I can as well compress it. By the time I take away the force, it goes back to its normal shape. Such a material is said to be an elastic material. Spring will return to its original shape, as discussed. If it returns to its original shape after the force is removed, it is referred to as elastic material. Most substances are elastic to some degree. Technically, a substance with high elasticity is one that entails a large force to produce a distortion on them. For example, a steel. A steel material will require a very high force to elongate it, just like the goldsmith does in their workshop. You have to subject it to high force before it can be elongated. In 1676, Robert Hooke, in his study, comes up with a law by observing the effect of tensile force on an elastic material. He noticed that the increase in length of a straight body is proportional to the force applied. He observed, like I said, that an increase in the length of the material that was stretched is proportional to the force. That is, F is proportional to E, where F is the force and E is the elongation or extension. And mathematically, it was further expressed as F equal to KE. And from that, he formulated a law called Hooke's law, which said that the extension E or X of an elastic spring is directly proportional to the force applied or load, the force or load, just like we have in the case of a spring on which a load of certain mass is suspended. is proportional to the applied force or load provided the elastic limit is not exceeded. What that law means is, as far as the elastic point of that material is not exceeded, the relation between force and extension holds. He expressed it, as I've given us before, as F equal to Kx. F is the restoring force that restores the material back to its original shape. K is the force constant of the spring measured in Newton per meter. X is the elongation of the material, otherwise known as extension. Now, from the formula F equal to Ke, an analytical pattern of the relation between stress and elongation is as shown in the graph. Stress is on the vertical while elongation is on the horizontal. But I'm going to take us through the term stress. Stress, when it comes to elastic material, is defined as the ratio of the applied force to the area. Stress is given as F over A, measured in Newton per meter squared. Now, looking at the diagram, we can see that as the stress increases, the elongation increases to a certain point. Between point 1 and 2, there is a proportional limit. The force is directly proportional to the extension as the force is being applied across it. At point 3, a yield point is being reached where there is no more proportionality between the force and the extension. Then, at point 4, we have a point of ultimate tensile strength. The material strength has reached its peak. Any attempt to apply further force will cause what we call fraction, which is shown in point 5. Now, Young modulus explains the relationship between the stress and the force. And the strain. Strain is the ratio of the length of the material to the extension, E, or elongation. And stress has no unit. So the ratio of the stress to the strain is what we refer to as Young modulus, which is given as stress over strain, which can be written as F over A over over as strain equal to L over E. L is the length of the material, E is the extension. Now, the relationship between stress and strain is referred to as Young's modulus, which is given as stress over strain. Stress over strain, which can equally be written as F over A over L over E. It can also be expressed further as Fe over AL. The unit still remains Newton per meter square. Now let's look at shear modulus. Shear modulus is also called elasticity of shape. Take for instance, I applied a force tangential to the surface of this material in any direction. By the time the force is applied, the end of this material are dislocated or distorted, and there is a change in the value of the length across the end of the material. So another way an elastic body can be deformed is by a shear stress. In this case, the deformation is due to an applied force that is tangential to the surface area as illustrated. Let's look at the shape on the screen. The effect of shearing force on an object. When the force is applied across the surface, there is a change in the position of the object along the vertex, as we can see change in X. So the object is deformed, and that change affects the liquid substance in the object. A change in shape automatically results into change in volume. The shear strain, which is given by X over H, where X is the relative displacement of the face and H is the distance between them. Just like we have in the case of the Young modulus, there is what we call shear strain and shear stress. The shear strain is sometimes defined in terms of the shear angle phi, where phi is in radian. The effect can also be considered when you are talking about volume force in compressing an object. When you have an object that has a particular substance inside, you can compress the object by altering the volume. Such a volume stress is frequently applied by pressure transmitted by the fluid. An elastic material will be compacted by a volume stress. That is, it will display a change in volume, but not in shape. When you compress it, the volume changes, but the shape remains the same. The change in pressure is equal to the volume stress, as pressure is given as force per unit area. The volume strain is the ratio of the volume change to the original volume. That can generally be written as this. For the volume, we have change in volume over original volume. And for the pressure, we have force. This is for volume. For the pressure, is given as force over area. So when we want to find the bulk modulus can be given as the ratio of the pressure to the volume or force to the volume, which can also be written as change in pressure over original pressure divided by change in volume over original volume. Now, let's quickly look at molecular properties of fluid. The molecular properties of fluid consist of viscosity. Viscosity is the internal friction in a fluid. Viscous force opposes the motion of one portion or layer of the fluid relative to another. Viscous effects are important in flow of fluid in pipes, the flow of blood, the lubrication of engine parts. They are very important application in that area. Another property is surface tension. Surface tension is defined as the energy needed to increase the surface area of a liquid by a unit of area. The surface tension of a liquid comes from an imbalance of intermolecular attractive forces, the cohesive forces between the molecules. A molecules in the bulk liquid observing cohesive forces with other molecules in all ways. A molecules at the surface of a liquid observe only net intermost cohesive forces. What do we really mean by cohesion? Cohesion, which is also one of the molecular properties of fluid, occurs when there is intermolecular attractive forces acting between two adjacent portions of a substance, particularly of a solid or liquid. It is this force that holds the piece of matter together. Adhesive forces. Forces is the forces of attraction between a liquid and a solid surface. The difference in strength between cohesive forces and adhesive forces regulate the conduct of a liquid in contact with a solid surface. So the difference between the adhesive and the cohesive forces determine the behavior of a liquid when it comes in contact with a surface. Some will wet a surface, while the other one will just roll on the surface. We have another properties of fluid which we call capillary action. Capillary action is the rise of a liquid that wets a tube up the inside of a small diameter tube. That is a capillary. When a liquid is placed in it, we can use this as illustration. Supposing I have a tube and there is a liquid that wets the surface. If the liquid rises in level after it has been placed in the liquid, such action is what we call capillary action. Thanks for listening.